Welcome to the ACIT Science Podcast, the official podcast of the Association for Critical and Interdisciplinary Thinking. We are a global non-profit organization dedicated to spreading education around artificial intelligence, neuroscience, and social change. In this podcast, we are hoping to provide insightful discussions with young professionals and world-leading researchers alike. I'm your host, Manuel Brenner, and now without any further ado, let's jump right in. Hi, welcome to the podcast, Alex and Ella.
Hey.
Hey.
Thanks
Hello.
for being here. Thanks for joining us. So I already know you guys quite well, but for our audience that is just tuning in, can you just give a short introduction, like what your background is, what scientific background, where you're from?
Yeah, absolutely. I go first. Manuel, thanks for having us. And my name is Eleanor Crane. So I'm a PhD student at the London Centre for Nanotechnology, which is a joint venture between University College London and Imperial College London. And I work with Professor Andrew Fisher. So I started out as an experimentalist, and I'm now doing more theory work on quantum computing in silicon, so in donor and spin qubits. So recently, and I just had a paper that came out, we were looking at a new form of entangling gate, which would have higher fidelities and which would be easier to implement and be more scalable in the silicon platform. And I've also recently been taken on with IBM part-time alongside my PhD to be part of the community and outreach team in the UK for the Qiskit open source quantum software package. Yeah, that's about it actually.
So yeah, I guess we get back to Qiskit in more detail later after the introduction, so let's move on to Alex and hear about his career and background.
Yeah, first of all, also, thanks for having us. My name's Alex Schuckert. I'm also a PhD student in Munich, in sort of the Munich quantum area, affiliated to the Technical University and also to the Max Planck Institute of Quantum Optics. And I'm looking into how you can describe the matter around us with quantum theory, and these are typically very hard problems which you cannot solve just by pen and paper or on a normal computer. But what we're doing now is we're using a very special form of quantum computer, which is called quantum simulator, to simulate these materials and find out about their properties and what their microscopic inner workings are. And for this, we are thinking about how you can do this experimentally. So I'm also a theorist, but more thinking about what you can do in experiment.
We are bringing this podcast out under the title Quantum Computing Podcast. So the overarching topic is going to be about quantum computing. But as we already probably noticed from your introductions, there might be different research areas involved in quantum computing and the overarching topic of quantum computing. So before we dive into the details of your research and like what is being researched at the front of quantum computing, can you maybe take a step back and take a look at what quantum computing is and kind of how it relates to what you more specifically do in your research?
Yeah, that's quite a convoluted question.
Sorry about that.
I think that's fair. Because there's a very strong link between quantum computing and quantum simulation, which is along the sides of what Alex does. I don't know. Do you want to make a comment about that? Or
yeah, sure. Yeah, I could say something about this. Yeah. I mean, quantum computing actually started out, or the basic idea started out with an article by Richard Feynman in the 80s, where he proposed the idea of a quantum simulator in the context of how you could describe fundamental systems described by quantum mechanics. Because at the time it was clear that if you take many quantum particles together, for example, atoms, and build a solid out of that, then it would very quickly become unfeasible to try and describe this with a normal computer. And so he had this very famous sentence in his paper, or I don't know even know whether it was in his paper or whether he said it in some talk, saying, if you want to describe a quantum system, damn it, you need to use a quantum system. And so the idea is to use one quantum system, which you can control really well in experiment, to describe a different quantum system, which you can't control as well. And one example is, so this is what, for example, people at the Max Planck Institute do, is that you try and describe how electrons move around in a metal or a semiconductor by making a model of these electrons with a different quantum system, in this case atoms. And what's really cool is you can actually show that the fundamental laws that describe electrons moving around in the solid is completely analogous to these atoms, which are trapped with light fields. And the amazing thing about it is that atoms are 10,000 times larger than electrons, but yet they are behaving according to the same rules. And because they're so much larger and so much heavier, they move a lot slower. So you can actually look at them moving around, which you can't do with the electrons in a solid. So this is the idea of a quantum simulator. You use one quantum system to look at a different quantum system.
So can we reapproach this question from what you mentioned earlier about what Feynman said about needing a quantum system to simulate a quantum system? So what specifically makes it so difficult to simulate quantum systems compared to classical systems, or to use classical computers to simulate quantum systems?
Yeah, the one way of seeing it is that if you take a classical system, or what for example Newton's mechanics, how describing the world works there is that you have kind of particles which whiz around in space, and what you need to describe the state of many particles within, for example, a room, like gas particles within a room, is only 6 parameters per particle. You need the positions, which are kind of the XYZ coordinate, and the velocity, which are the XYZ coordinate of this velocity. And if you put many particles together, then the problem doesn't in principle become more complicated, because you just, when you have 10,000 particles, you just need 10,000 of these coordinates. So in total, 60,000 parameters for 10,000 particles. But if you take a quantum system, then that is not true anymore, because a quantum system can show a property called entanglement, where the properties of one particle depend on the properties of another particle. And so in order to describe a system of 2 particles, it's not only just that you need parameters to describe them, which is just the parameters of one particle and the parameters of another particle, but also parameters which describe the joint state of the 2. And what it means in practice is that the number of parameters that you need in order to describe a system of n quantum particles actually increases exponentially with the number of particles. And I think now with COVID, people know what exponential growth means. But that it becomes quickly unfeasible. So I don't know, Ella, I think you were recently thinking about how many qubits can you actually still store in a normal computer? Something like how much, like just in the ballpark number?
Yeah, I mean, at the moment, if you have, for example, 2 qubits, that might take, for example, 512 classical bits, or 3 qubits, you need maybe 1,204 bits, because in a qubit represents a state of a quantum particle. So whereas a classical bit, you just have up or down, or you just have 0 or 1, like in a computer. That's how computers are coded, in zeros and ones. Then in a qubit, you have you can make the most of superposition, which is that an electron, for example, can not only be in spin up or in spin down, but it can be in a little bit of spin up and a little bit of spin down. And it's just when you measure it that it collapses to a single state. And so if you want to represent that information in a classical way, then you need a lot more classical information, of course, to have an understanding that you're in a little bit of both. So you generally need 2 to the power n classical bits, in a way, or classical bits of information to represent n numbers of quantum bits. And also as a comment, just because it was niggling me from earlier, is because we always say that Feynman came up with the idea for quantum computation or quantum simulation, and it's probably it was just in the air at the time, or something you always see in science and in a lot of different areas in the world is, ideas just start emerging from collective thoughts, and a lot of the work which was put into bringing even Feynman to being in the right place to be able to think of those ideas was put in collectively. It was collective work. So there's probably a bunch of other people who were also thinking similar thoughts at the same time, but Feynman definitely is given a lot of credit for having said that, and luckily he did, because it's given rise to a lot of good work. And maybe, I don't know, Manuel, if I can also just mention on the topic of quantum computation and why what it is, or why that's interesting, because it's linked in with the concept of superposition. But what a classical computer can make use of, what a quantum computer can make use of, which a classical computer can't, is exactly this phenomena that a qubit can, when it's in its fragile quantum state, be in a little bit of 1 and a little bit of 0 at the same time. So it can be in superposition. And when all of the qubits in the computer making the computation, they are actually in all of those states at once. And so you can imagine the amount of extra power that you get over a classical computer. But the problem is you can't actually choose which one of those intermediary states you're making the calculation in. It will just collapse. The measurement will collapse when you make a measurement. The state of the qubits will collapse randomly to any one of those states. And so that's why it's a little bit tricky to make quantum computation, because you also need to make use of interference effects. So you can make use of the fact that all of your qubits are in superposition, but you need to kind of make sure that they add coherently to bring out and highlight one of the useful states that you need. So that's what a lot of the quantum algorithms, like the Dutch-Jozef algorithm or the Shor's algorithm, they all make use of interference effects. So they're all basically clever ways of exploiting superposition. Basically, quantum computers give us a good advantage, but you need a clever way to ensure that the right result comes out. Yeah. Otherwise, you just...
Yeah, so if you compare it to the output of a classical computation, which can be described by a Turing machine, for example, in which the output of the computation is simply given in the symbolic language, which is usually just a string of 1s and 0s. So you have a fixed and determined outcome of your computation, and you start with a fixed and determined input of your computation. And while the computation is going on, you can at every step of the computation trace the information content of the computing device, so of the Turing machines, of the tape. So in a classical computer, that would be analogous to knowing what's on the hard drive, because everything is encoded in 1s and 0s. And in a quantum computer, this is very different, because the information is contained in the wave function that you can't directly access, but only in the end carry out a measurement, which is inherently non-deterministic, but has this weird quantum property of stochasticity inherent.
Exactly.
Yeah, it's also one way people talk about the power of quantum computation is in terms of complexity classes. And there, it's also not quite clear what additional problems we can actually solve with a quantum computer, because it's also always the question, what you just said is as well about a Turing machine. You always know whether you got the answer or not. But with a quantum computer, there may be problems where you know the answer with some precision, with some probability. So you now have this very kind of weird situation where you can come up with problems where it's very hard to know the answer precisely, even with a quantum computer. But with a quantum computer, you can know the answer with some probability, which is maybe very close to 1, but not exactly 1. And you can get that result easily.
So recently there has been quite a lot of hype around the claim of Google to have achieved quantum supremacy. So the question of quantum supremacy also kind of hints at the question of what quantum computers are actually useful for, and in what sense they can be seen as like beating classical computers at some kinds of computation. So can you first address what quantum supremacy actually means, and like also elaborate on the question what the potential usefulness of quantum computers could be?
Yeah, so quantum supremacy is a term termed by yet another famous physicist, John Preskill. And before I talk about it, I just want to quickly mention that it's a term which is also heavily debated among physicists, whether we should use it or not, because of supremacy also having other connotations. So in Europe, people usually talk about quantum advantage, or So I like the word advantage more, and it's also somewhat explains it more what the principle is, namely that there may be problems where a quantum computer can get the answer to a problem quicker than you could do that with a classical computer. So that's a, let's say, classical way that quantum advantage or supremacy is explained. So, for example, the classic example is factoring. So factoring is the problem where you have a very large number and you want to decompose it into its prime numbers. So, for example, 15 would be 5 and 3. And this problem is very important because all of our encryption mechanisms that we use today are based on the fact that it's very easy to multiply prime numbers together to get a very large number. But it's very, very hard to factor this large number into its prime components. And this is this is what encryption mechanisms need. They kind of they need to be easy in one direction and very hard in the other direction. And so there is a quantum algorithm. So there is a quantum algorithm which does the factoring problem very quickly and efficiently. And so people say this quantum algorithm has a quantum advantage over the classical algorithm. Yes, but there are more dimensions to this question. So one is, and this is something that that Google is advertising a lot, is that quantum computers, even if they're not faster than classical computers, they might be more energy efficient. So you may have problems where a quantum computer does it in the same time as a classical computer, but you would need much, much more energy resources to get to the answer. So even if it turns out that quantum computers never get to the stage where they are very useful in the sense of getting the answers of new problems, they might just save us a lot of energy.
Would you comment, because obviously if I'm employed by IBM, I don't know if I can quite comment in the same way, but did you read about IBM's answer to Google and their classical algorithm, or not classical, but they'd found an algorithm which was much more efficient than the one that Google was comparing to classically?
Yeah, so Google made this claim last year that they had reached the first time reached the quantum advantage. So for the first time, they had done a quantum computation which would not be possible on today's classical computers in a reasonable time. And the way they did that is
10,000 years, I think, was kind of the ballpark figure that they said it would take
exactly.
on the best quantum, like on the best supercomputer we currently had.
Exactly, yes. It was. So one thing one has to mention is it's a very artificial constructed problem. So it's not a problem which will be useful to anyone anytime soon. But it's really a problem which which was constructed by Scott Aronson, a complexity theorist, to address exactly this problem of quantum advantage. And so now basically IBM, one of the main companies which have been involved in the quantum race from the start, very quickly after the paper came out, put up a blog post where they said, oh, we actually came up with a classical algorithm which would do the computation in 5 days instead of 10,000 years. And and the reason why they were able to do that was because the classical algorithm by Google used only the memory, like the fast random access memory of the supercomputer, to store the wave function. So this is what Ella mentioned earlier, that you need a very large memory to store the wave function. And so when you have many qubits, then it becomes very hard to store that wave function. And IBM came up with an algorithm where you store the wave function partially in the hard drive of the classical computer, which makes it a lot slower, or well, not slower, but I mean in this case somehow it reached a speed up of the algorithm, and so that yeah, and I think this problem or this discussion really beautifully kind of illustrates the position where quantum computation is right now, namely that there are algorithms which are faster than the classical algorithms that people know so far. But for most of them, it's not clear whether there is maybe a classical algorithm which is as fast as a quantum algorithm or even faster.
Yeah.
So there are now so-called quantum-inspired classical algorithms, where people use concepts from quantum computation to come up with a lot of classical algorithms which are a lot faster. And yeah, but there is at least one problem where it was shown mathematically that there is a quantum algorithm which is faster than the fastest possible classical algorithm. So this was proven by Robert Koenig. He's a mathematician in Munich, and he really showed that there is no. So I mean, this was again a constructed problem, but it's with this proof, it's definitely clear that there is no kind of barrier, or that let's say in terms of complexity, the complexity classes of easily solvable quantum problems is definitely larger than the ones of classical.
You mentioned this problem being quite the artificial problem. And sometimes with these like very specific applications of these quantum algorithms, it's not on first glance apparent in what sense they could provide some kind of usefulness, or if the complexity class of the problem they are addressing kind of also contains a lot of very useful problems. So can you kind of, talk about in what sense these benchmarks that are being achieved right now have some relationship to actual real world applications that could potentially impact societies as well?
I mean, there's a nice website called Quantum Zoo, which you can go on, which is actually a repertoire of all of the quantum algorithms which have already been talked about. And there's already algorithms for efficiently factoring large numbers, Shor's algorithm. So that's also where a lot of this cryptography, a lot of the questions around cryptography are coming from, and searching an unordered list in ON time. And there's a lot of, I think actually one of the main areas where quantum computation will be very useful is the rather obvious one of simulating quantum systems, using a quantum system to tell us exactly how a quantum system acts. And even if that's the only place where quantum computers are useful and we're not able to encode larger mathematical problems, belonging to the NP or NP complete class inside it, then that's also that's maybe okay, because we're going to learn a lot even just through this understanding of what quantum systems are, because currently it's so difficult to do many body quantum problems on classical computers. So, but it's predicted also that quantum computers will be able to help us find materials for carbon capture. There's a lot of quantum chemistry going on, or efficient fertilizers, or managing risks and opportunities related to financial portfolios, discovering maybe new drugs and protein structures. Also, it'd be possible to optimize supply chain and logistics. So it's really got a lot of different areas where the different types of algorithms could actually be applied. And yeah, I think maybe this fundamental questions about the universe thing, really, of how matter behaves at the atomic and subatomic levels, is maybe one of the most interesting ones.
So let's zoom in a bit on that question of actually simulating quantum system with quantum computers / quantum simulators. So you already mentioned a couple of applications, for example, quantum chemistry, simulating the proteins and simulating how proteins could interact with synapses. So I guess from everyday life, people don't really have a strong intuition what constitutes a quantum system and in what sense quantum systems actually play a big role in our life. So what are actually like very interesting quantum systems that you could imagine simulating and gaining important insights that have also some like applications?
Yeah, so let's say there are two maybe quite distinct directions which people follow right now, but which in the end kind of belong to the same problem class. And one of them is explaining matter on a fundamental level and trying to find, and by understanding this matter, finding new materials with very exotic properties. So one example, which was also quite hyped in let's say in the last 10 years, and which is also funded by the EU quite heavily, is research into graphene. So graphene is a material which is made out of carbon atoms, and the special thing about it is that it's perfectly two-dimensional. So it only it's exactly one atom thick, and graphene is not the only material now that people are exploring. There are many more two-dimensional materials with very exotic properties attached to them, and people are using quantum simulators in order to understand materials like graphene, but also a special class of materials called high-temperature superconductors, which might really revolutionize the way that we transport energy from A to B. So, for example, so to explain it a bit more, because it's really, high temperature superconductors are one of the main motivations for doing quantum simulation in the first place. So what is superconductivity? That's the property of material to conduct electricity without loss. So you can really make you can really transport energy without any loss over arbitrary distances. And this effect is really a pure quantum effect. So you cannot explain this property by classical physics. And it's also a many-body effect. So it's an effect which comes about because electrons are interacting with each other in a very peculiar way. And superconductivity has been found decades ago, and people are understanding normal superconductors quite well. But the problem with them is that they only show this property at extremely low temperatures. So at temperatures of just 4 degrees above the absolute zero, so minus 260 or 65 degrees. And so it's not really feasible to build a cable out of this material and then make it superconducting, because you would have to put an enormous amount of energy in cooling it down in order for it to show this property. But now, actually, around the same time that quantum computing or quantum simulation was thought about the first time, people discovered materials which conduct electricity, which become a superconductor at very high temperatures. So high means only at minus 100 degrees, which is important because now you can use different coolants, which makes it more energy efficient. Um, and despite the fact that people have really tried understanding these materials, they haven't succeeded so far, because it's really an extremely difficult to solve problem in the sense of being very quantum mechanical. So you cannot just simulate this material on a normal classical computer. So what people are doing right now, for example, in Munich, but also in Harvard and many other places, is to build a quantum simulator to describe these high temperature superconductors. Um, and the way that they do it is they create with light fields, so with lasers, basically they create a potential landscape, so a bit like hills and valley kind of structure with light. So it looks a bit like an egg carton. And in the valleys of these egg cartons, they put in single atoms. And these atoms, now it turns out, interact with each other in exactly the same way as electrons interact with each other in these high temperature superconductors. And so by looking at these atoms trapped in light fields, you can now quantum simulate a high temperature superconductor and really understand what is going on. And so, yeah, this is one of the directions that people are using quantum simulators today already to understand exotic materials. And it's let's say quite easily conceivable that if we succeed in understanding these materials, then we maybe also get a recipe how to create a high temperature superconductor which has this property at even higher temperatures, so even at ambient room temperature, which means we can really conduct electricity anywhere to anywhere, any place in the world without losing energy, which would be very cool, I guess, also for energy problems.
Could
Yeah,
imagine like on a specific place on Earth where the sun is shining for the entire year, you could just build a big assortment of solar panels, and if you had the
exactly.
ability to transport energy across the world without any friction, without any loss of energy, then you would just
it's actually even the superconductors that we have today would actually be enough to do this kind of thing. And it's so I read, and I'm not sure how correct it is, but that the technology of superconductors was just maybe about 10 years too late, because energy companies had already decided on using high current DC lines to conduct electricity over long distances.
So you mean that like you could build a superconductor that would be cooled, but it would still be more efficient to cool it down if you have just a lot of currents flowing through there?
Yeah, and it would be not only more efficient, but also it would be much easier to do that. So you could really use just one cable with maybe 30 centimeters diameter to conduct as much electricity as these huge, like 200-meter tall power cables that kind of go through the landscape.
Okay, that's crazy.
And you could put that kind of below the road, so no one would complain about it and all that. So, but I mean, it's still in kind of an exploratory stage, and so that's why people are not using it yet, because you need to put a lot of money into finding out how to do that on a large scale. Yeah. But anyway, coming back to the quantum simulator, the second direction that people are looking into is quantum chemistry. And that is sort of what people think is the first real application of also quantum computers, to distinguish them from quantum simulators. And quantum chemistry is the problem of describing molecules and atoms on a fundamental level, which is also very hard problem. And when you think about molecules, then, when you can describe very large molecules, then you can go into the direction of large biomolecules. And when you can describe biomolecules, then you're very close to being able to describe proteins, and that would be very cool for kind of drug design and things like this. So that's where the motivation for this is coming from.
So just to reiterate, you mentioned in the beginning that you can model the behavior of electrons in superconductors with the help of ultra-cold atoms. So the kind of the connection behind that is that a lot of quantum systems that might seem very different on first glance have some, like on the fundamental level of the laws that govern their behavior, they might be very similar, and that's what makes it so useful to use one system that you can easily control to simulate a different system that might be a lot more difficult to control. So Ella, you mentioned as well that you worked more on the experimental side in designing these kind of like hardwares that could allow us to implement more stable quantum computers. So can you talk a bit about what you did there and what kind of the technologies are from the hardware perspective?
Yeah, one of the frameworks which my group works with, for example, is actually using the electrons in silicon. So a lot of this kind of Hubbard problem, which is the name physicists also talk about the science that Alex was mentioning a minute ago with the superconductor. So a lot of that problem actually comes from what's called donors in semiconductors. And so essentially doping silicon with phosphorus is what's always been used to make computers. So all of the transistor devices there, there's tunnel junctions in there which are created with the transistor device is created with a heavily N-type doped semiconductor structure, which means that you add in to a crystal which is lots of atoms which look exactly the same, and then you swap one atom out in the structure with an atom which has exactly the same number of protons and neutrons and electrons, plus an extra proton, extra neutron, and an extra electron. And you can kind of approximate that the core of that atom with the extra proton and neutron are pretending to be similar to the core of all the other atoms in the crystal structure, but the extra electron is free to move because it's not being bound. It's not all the other electrons which are surrounding the atom are being used to hold on to the other atoms in the structure and create the crystal. So they're all kind of in use. But because the phosphorus has one extra electron than the rest of the silicon, that electron is free to move around. So that's the electron that we're looking at in our group to use for quantum simulation and for quantum computation purposes. So that electron has a spin, so that the spin of that electron can be used to make a qubit for a quantum computer. And in the context of a Hubbard problem, for example, Nguyen Lei just published a paper recently also about how you could encode the Hubbard problem using phosphorus donor spins in silicon. And you can exploit all sorts of, or not exploit, that's not a very nice word, is it? You can make use of or lever or you can work with the electrons in the solid to look at, you can excite them to different excited states and have different magnetic pulses in order to be able to apply the right Hamiltonian, so to be able to have the right chronology of forces applied on your system, that it can act in a way to tell you about the exact mathematical framework which you were initially questioning it about. So, for example, semiconductors, donors in semiconductors is one option, but then there's many different options like Rydberg, ultra cold Rydberg atoms, or ions and ion traps, or superconducting qubits, which are more made from Josephson junctions, which are also actually in the solid state in silicon, and they're made with very much semiconductor fabrication technologies, but they're as far as my understanding is, superconductors are much more used in quantum computation, not so much in simulation. Do they use in quantum simulation superconducting qubits? I don't think so, right?
Yeah, a little bit as
A little
well.
bit?
Yeah, because they they implement a certain variant of the same model that you use to describe superconductors, kind of the bosonic version. So, um, so, so one way you can see a superconducting qubit device, which is what IBM and Google use to build a quantum computer, is that you have particles of light, which are called photons, which move from these superconducting qubits between these superconducting qubits. So they hop around between these different places, and then if there are two photons in the same superconducting qubit, then there's actually an energy penalty ascribed to that, and so that creates a nonlinearity. And this is something that is very difficult to achieve in free space, because photons usually don't see each other. So this is basically what people call the impossibility of building a lightsaber.
Yeah.
Because photons don't interact with each other. Only if you have really, really strong electric fields. Yeah.
So Star Wars is fake, is what you're saying.
At least you would have some crazy light source in that lightsaber in order to really build
Okay.
one.
This might be very disappointing for some of the listeners.
Yeah. Well, I think no one ever claimed that Star Wars is happening now.
Yeah, maybe. To summarize what the central point of being a quantum computer is. So you mentioned that you have a certain quantum system, which is usually a spin or some kind of quantum property that can serve as a qubit. And then these qubits can contain all the information that is being processed in the quantum computer, and then you implement what you mentioned earlier, Hamiltonians on that. And so in non-mathematical, non-physical terms, that just means you do something to the system to change its state and therefore change kind of the information it contains. So you can implement these Hamiltonians with magnetic fields
or electric pulses, yeah.
And again, the hardware that you're using can vary between silicon-based systems or, for example, atoms or some kind of spins. But moving from that hardware layer to a different layer, how do you connect kind of the quantum algorithms that you have with the hardware implementation, and how do these layers kind of interact?
Yeah, so that's very much what that does actually literally happen to be very much what Qiskit is. It creates a framework which has different layers to connect the hardware to the software, and to have a user end system where you don't need to think about exactly how long the light pulse will actually be applied to or how long the electric field will be applied to whatever system it is that you're using as your quantum computer. So there's different components to Qiskit, and so they use the words terra, air, ignis, and aqua. So from the very low level, very near to the hardware, there's terra, which is the earth element, and that's really kind of the bedrock for composing quantum programs, and that's thinking about circuits and pulses. So that's how the circuit that's been encoded on the quantum algorithm level is optimized for the constraints of a particular device, and managing the execution of batches of experiments on remote access devices and things like that. So Terra is what would be used and adapted to different quantum devices if you were going from a superconducting device to an ion trap device or something like this. And then there's air, which is for classically simulating making a simulation on a classical computer of whatever it is that you want to be running on the quantum computer, so that you can double check the results that you would expect your quantum algorithm to have, and you can also make noise models on that. And then IGNIS, which is the FIRE, is for helping to design quantum error correction codes. Or if you wish to study or characterize errors through tomography, for example, or finding a better way of using gates. And then finally there's aqua, which is water, which kind of permeates all the elements, and that's really for accessibility, and that's the top level. So that's if you work in finance and you also would like to make use of some of the aspects of quantum computing without wanting to understand exactly how all of those lower levels, Ignis, Naya and Terra, really work with the quantum device. So then you can use Aqua, and that's kind of a nice interface for just being able to see how you can adapt your problem to quantum computing.
You mentioned this interface is implemented in Python and accessible open source.
Yeah, I mean, it's implemented in Python, but you can also have a visual interface where you can slide the gates onto what's a bit like a sort of, looks like a partition of music, where every different qubit exists on a line, and then it's and they're all horizontal lines, one above each other, and that's the kind of chronology of your quantum circuit. And then you can add, just like in classical computation, you have you've got a bunch of different circuits, right? There's constant 1, constant 0, identity, and negation, and from there you can make all of classical computation. And similarly in quantum computation, you have a bunch of basic gates. Thinking there's loads of interesting things that you can talk about, like they need to be time reversible in the quantum in quantum mechanics. Things are time reversible, so you can't use those classical gates. But anyway, I'm getting a bit waylaid. But
yeah. But then, like, if you have those gates in front of you, or if you have the Python package in front of you, like, how do you approach framing a certain problem in terms of a quantum algorithm, or is that also in some sense automated?
Well, so you do need to get around. There's definitely thought involved in being able to think about how you best create a framework for your problem in terms of quantum mechanics. So if you want to create a superposition between your qubits, then maybe you'd use a Hadamard gate or something like this. Or if you want to entangle your qubits, then you want to use a Hadamard gate and then a CNOT gate or something like this. But it's also about being able to exploit interference to make sure that you actually get an interesting result from your quantum algorithm. And there's a lot of resources out there which you can base your work on. So you can look at what type of problem you have, and you can figure out from there also what the most strategic way forwards would be to encode that into a quantum algorithm problem. And there's also a very large network of quantum scientists which is out there. So there's all sorts of Slack discussions exist on the Slack network where you can ask questions. So you're kind of not alone, and there's a lot of documentation that you can refer to if you want to formulate your problem in terms of quantum mechanics. A lot of pre-made solutions also out there.
So it sounds like the research institutes and the big tech companies are going hand in hand in driving forward this research and creating these interfaces and this infrastructure to drive forward quantum computing research. So who would you say is most responsible, or like the driving force behind creating this kind of infrastructure?
Which infrastructure? I mean, on the topic of big companies, there's probably quite a lot of interesting quantum algorithms out there which are in development. And if you find a good algorithm which works for trading, then you probably don't want to go sharing about it and writing about it. So there's maybe some which good ones are being developed out there, but we don't know. But so the infrastructure of Qiskit, or
No, I meant in a more general sense. Who's driving progress in that area? Is it mainly the universities and the
Oh,
university-associated research institutes, or is it more the big companies, or is it just a very closely linked and tied together interaction between the two?
I don't know what you think about this, Alex. I think this it's quite interesting because it's really one of the areas in science where there's a very, very tight collaboration. So a lot of big companies like IBM and Google and Microsoft really have their own research labs embedded within them, and they in the end carry out their research similar to the academics, and then everyone meets at a conference, or everyone publishes their papers on the archive, or publishes their papers in whatever journal of choice it's going to be, which then gets read by the rest of the community and helps drive a small area of research which you probably weren't carrying out yourself, hopefully. So I think there's quite a lot of power being put into this research from the big companies and this is helping also academics obtain grants, because they're saying, well, look, this is obviously something which is of interest. And so it's difficult to say, is it being driven by a specific lab or not? You can look, I mean, a lot of academics are also creating startups. There's Lukin, also great work on quantum computation with Rydberg atoms, and I don't know, is he at 52 qubits now? And good structure there and good logic, and so he's also making a startup. So it's a kind of companies are also doing academic research, and academic researchers are going into making companies. It's really making a big mix. I don't know, what do you think about this, Alex?
Yeah, totally. I think it's a really interesting time where this research is kind of going out of the universities and going more towards being used in a more company-like structure, and people are still trying to figure out how do we do this work most efficiently. There are some people who say quantum computation is now just an engineering problem. Now you just need to scale it up, and we leave that to the engineers. But other people say, this is maybe thinking about it in too simple terms, because you also need to think about how you use quantum computers in the end, and that's more difficult. And maybe there are really physical challenges which also come up, and so there are now new study programs which pop up, which combine physics and engineering. So, for example, I think in Australia they have a quantum engineering study program now, and I think in Munich this year they are also going to start one. So there's now, really work put into create the new workforce, which are really going to build quantum computers from an engineering perspective.
Yeah, it gets close to material science, right?
Yeah. Because so far it's more physicists who try and do the job, but it's maybe a bit hard for scientists to do that because they think in different terms to engineers.
But there's a free flow of researchers between companies and academia and companies. So
Interesting dynamics, but I guess it has also been historically kind of this interplay between companies and the governments and the scientists has always been present, also during the 20th century with von Neumann and Turing. Like, also the foundations of classical computations are always centered around applications for the military or applications for companies. So I guess
that's true. Yeah. I mean, these foundations were really one of the places was the Bell Laboratories, where the notion of entanglement was maybe really developed in really important ways with John Bell, and it's true. But it's I think what's quite cool about the development right now is that that it's really close to kind of internet companies or software companies, where the notion of open source is something quite important, and I think it's really amazing what for example, IBM is doing there, and Google, they also have a similar program called Circ, which is also open source. And they're really trying to keep quantum computation as something which is a common resource that everyone can try out, and which is maybe also not bound to the resources of developed countries. I think you mentioned the other day that in India there's a huge quantum computation community, or
Yeah, huge and growing.
yeah, without them needing any resources apart from maybe a laptop, and you can run programs on the IBM machine.
Yeah, there seems to be a similar dynamic going on as in the machine learning community with the big packages, PyTorch and TensorFlow by Facebook and Google respectively, also being made freely available, and computational resources on servers also being very cheaply or even freely available. And you can kind of observe this democratization of like computational power, but also kind of brain power of people from all over the world, especially a lot of people in India joining in and programming and kind of making the best use of these tools.
Yeah.
Switch gears a bit and move to a more personal perspective on the subject we've just been talking about. So you both have been doing research for a couple of years now, have been pursuing your PhD and living the researcher life for a while now. So I think it's really interesting to see what kind of drives people into that direction and what their daily experience with research is. So are there any big lessons you have learned while doing this job for the last couple of years?
I feel that's a good question. I feel like I'd like to say something about teamwork, but I'm not sure what yet. If you're not burning to say anything, maybe I enjoy the fact that in academia there's a lot of freedom, freedom to pursue any research objectives which you think have weight if you're in a supportive environment and you're with a group that provides you with support for doing that. And it's really exciting to be able to work with other people who are happy when you make advances in your own work because it brings forwards a collective project. It's also exciting when you go to a conference and you present some results and it turns out loads of other people are equally as interested as you are in not only the field but also what advance you've got, and you can see that questions that you were asking yourself other people have been looking into. And so for me basically it's very exciting, and it's been very nice to see also the contrast with the kind of corporate world and working with IBM, where in a way in academia sometimes some of the fascination occasionally seems like it dies out very slowly because it's their everyday lives is research. So if you do something every day, it's a bit like having Christmas every day. It's great, but you kind of get used to it a little bit. And it has been lovely working with the team at IBM because everybody has a lot of energy. Maybe the general age range with whom I work is slightly lower, but everyone is quite excited to be able to help everybody out. It's also teamwork, and maybe I'm also in a different area, outreach and community, but it's much more structured. So we know a lot more where we're going with things. So we have aims and objectives, but that's something to doing that as well, because you're able to pace yourself better. So it's been exciting to see the difference between the two. What about you?
Yeah, I think this is similar to what I experienced over time, so in the PhD, because I know or at least when I started my PhD, I had already done a bit of like 1 year research within the master thesis, or like tried it out a little bit. And when you finished your first project, you can kind of fall quite quickly into the fallacy of thinking, oh yeah, now I know how research works, and now it's just the same thing and repeated a million times, and then you get the Nobel Prize. But but I think there is something there that when you start thinking about problems, then no, or put differently, if you when you start working in research, you think, or at least, yeah, when I started my PhD, I thought, yeah, so now in your PhD, what you're supposed to do is you create knowledge which hasn't been there before. Because so far in your studies, you've just learned what other people had done, and you just had to reproduce that more or less. And so I thought that would be the really difficult thing, would be to find out something new. But now over time, it turns out that it's actually not that hard to find out something new, because actually people don't know very much about anything. But what is actually quite hard is to find problems which are actually meaningful, and which are important to work on. And so, yeah, now I feel a bit more that the actual difficult thing in research is to work on problems that have some impact on research or humans in general. Because you can do very easily, you can work on very complicated problems and then bring out a paper which has a lot of formulas in it, and people think, wow, this person is really smart. But it might turn out that this is not very useful to do in the end, and no one really cares about it. And so this was, yeah, more of a, yeah, later thing. Yeah, but yeah.
So were you mainly driven into research out of this ideal notion of just the pure joy of finding something out and the pure joy of like deepening our understanding of the world, or was it more like, or has it kind of shifted now that you have been working in research to a more pragmatic notion of helping people and maybe helping people in the community and just having that more like goal and application oriented vision of what you're doing?
Yeah, I thought it would be really nice to classic answer, but it's true, to help the world, to do something useful for the world, and it just, and then if you do something, you do a certain amount of helping people on a small scale, or maybe humanitarian work directly or something like this, and it's ever so, it's a little bit heartbreaking, because you wonder, you live one short life, help a few people, and maybe and I guess for me, science was a way of finding a different balance, of making very, very small steps forwards, but which might reach which might kind of involve all of us and what their outcomes might be. So although the difference that you would make to one person would be much, 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 much more tiny, it would be infinitesimally small, then it's more even. The problem for me with working in science is, it's great, okay, we work towards making a quantum computer, it's so exciting, maybe we're going to solve some real fundamental problems that we have, understanding how atoms and molecules work and what the fundamentals of the universe really are, and that's very exciting. Maybe you can work on how proteins attach better to cell membranes and things like this. The problem is, how does the actual results of your work get used? It's, if you work with people directly, you really know the end of where, you know exactly who you've helped and how you've helped them. But if you make a quantum computer, it can then just fall in anyone's hands. Maybe then you just help some awful political system get a lot more power, and that side of things is quite tricky to work on. It's quite tricky. Inner debating is going on there.
Yeah, and I guess in the everyday life for researcher, it's also easy to get lost in your microcosm and to not really see the relationship between what you're doing and the real world out there, and potentially even harmful applications of the technology you're
I think that's also what
creating.
pushed me to go more and more from my materials research more and more towards quantum algorithms, because I thought if you can, you're still early days for quantum algorithms now, and it's the people who work on quantum algorithms today in a way who get to also to a certain extent decide on what problems quantum computers will solve first. So it would be nice to help the push in the right direction from the point of view of that.
Yeah. Yeah, for me it was very, very I was mainly driven about fun in the beginning. I was
great.
just kind of working on problems which I had some sort of fun with, in the sense of I learned certain skills in university, and then I wanted to use these skills, and I thought, oh wow, now I can actually find out something new. And so I just continued exploring a bit, and that was quite satisfying for a while. But now I really feel that it would be quite nice to do that in a way which would then be rewarded by seeing those ideas or this work be used by others in some way. So may that be in within a research community where other people would say, oh yeah, this is actually quite interesting, let me develop on that, or actually out there in the real world, in some technical application or something like that.
So you just have fun all your life. It's just a holiday. Constant holiday.
Just
Yeah, that's neat.
just explore a bit.
I'll try and learn that from you.
But yeah, at some point you also need to explain why you're doing these things to other people. In the latest stage, when you want to get funds from people to continue your research, and and I think that it's quite good to think about these questions.
So I guess on the other hand, there's still this more kind of naive joy of finding something out. There's pure mathematics. There's theoretical physics in the areas of string theory, where you have like pretty low chances of actually finding some useful results, but you have beautiful theory that you're pursuing. So would you say that has shifted more towards like the practical side and kind of this feeling of having to justify what you're doing to yourself and to society, or is it still kind of this pursuit of pure knowledge?
Yeah, I think both. And I think you never know when something will be useful or not. In fundamental research, I think if you would just follow ideas that are immediately obvious to be useful in some technical application, then a lot of the things which are now useful for technical applications wouldn't have been found. But the thing is, you never know. So it might be, you're working on something that you think might be useful, and it turns out not to be useful, and the other way around. So I think having a technical application in mind is not a motivation which will help you in the short term. So really thinking about more fundamental questions of science in general, as something that kind of follows human curiosity, almost like a cultural good. To me it's almost like making a piece of art or like a piece of music. It's something that humans do because we are able to do it, and for no other reason.
Yeah.
And that's quite nice.
Yeah, I think that's kind of beautiful. So this has all been extremely interesting. But before we completely wrap this up, I just have one more vague kind of philosophical question. Like, if there's just one big scientific question that you could have answered right now on the spot, what would it be? So what is to you kind of the most fascinating scientific question that is yet unsolved right now? Intense.
There are
break.
so many that I don't.
Yeah.
I don't know which one. Yeah, I think it would be really neat to understand how high temperature superconductors work. I think that will be a huge leap. I think someone estimated how many papers have been written about high temperature superconductors, and I think it's something in the ballpark of 100,000. So I think it's something which would be really cool to understand.
For me, I might be trending topic today, but gravity. That would be one which would be quite good to know a bit more about.
Yeah. to put it mildly.
Yeah. Cool. But thank you, Manuel.
Thanks. It was just a very interesting conversation, and
thanks very much for having us.